Okay, let's see if we're recording. Yeah, looks like we're recording. So here's the repetition on the worksheet that you did this morning in class. So I'm just going to do them. Hopefully we've had some discussions individually and as a group on some of the things that we're starting to work with. All right, so linear function through 9, 7. 9, okay, I'll get rid of that. And what do I want? I want to get a 7. Oh, looks like it's a little subtraction made that happen. Just get rid of something, bring in what you want. That's kind of nice and easy. And then we're gonna go to the number 15, which means there's 6 units of change here. I don't know if I'm gonna change from 7, 6 units from 7. I haven't even seen what my next Y value is. So let's turn it into the number 1. And so that if 6 doesn't work, we'll bring in something that does. 12. Oh, well, 7 to 12 is 5 units, not 6. All right. So I've now converted the 6 units of change into 5 units of change, tacking on to 7, and that's how that function works. Well, of course, if I saw that, I would immediately see 9 as a critical number, up 7. And then if I horizontally change by 6, and I didn't want a vertical change of 6, if I wanted a vertical change of 5, then I got to knock it down a little bit. Bang, there's your linear function. All right. Next problem. Quadratic, -2, 3. So a quadratic is squaring change, and I want to square change from -2. So I'll write x plus 2. Okay, because now when I put -2 in, I get 0. 0 happens to be a minimum, right, of the squaring process. We'll be talking about that in class briefly. And -2 gets me 3. Well, right now it gets me 0, but I got a marker, which is what mathematics is all about. And now I've got correlation, where a -2 gets me a 3. It's also the vertex, because the vertex of a quadratic occurs when you square the number 0. And so I made -2 become 0. Okay, I got a minimum. What am I passing through? I'm passing through 117. I'm going to put a 1 in. Well, the change is not, this is not where change is occurring. Change is occurring here. When I put a 1 in, 1 plus 2 is 3. 3 squared is 9 units of change. I don't know if I want 9 units of change, so let's get rid of it. Find out where we are headed. We're headed to 17. Oh, so if I went over 3 units and squared it, I should go up 9. You know, I should go up 9 units when I square 3 units of change. But looks like I need 14 units of change. Well, I guess that's a little bit bigger than a 1 times 1 multiplication. I'm not sure I wanted to say it that way, but that's your equation. So over here, we started at -2, 3. Going over 3 units, should have gone up 9, but it really went up 14. So it's a unit converter. All right, so that's that problem. Let's see, what's next? What other one did you do in class? You did log 64 of 4. So we want to know 64 to the what equals 4. I can't say anything because they're not the same base. Oh yeah, 64 is 4 cubed. I can do that. I know 4 is raised to the 1. Oh, it sure looks like the exponential activity. Multiplication. 3x equals 1, so x equals 1/3. So now we look at it conceptually. 64 to the 1/3. What does that mean? It means the cube root of 64. What times what equals 64? And it sure looks like it's 4. So the answer to this was 1/3. Take the cube root of 64 and you get 4. All right, so did that one in class. Hopefully that means a little bit more to you today than it did on Monday. Log base 5 of 1 over 125. Log base 5 of 1 over 125. I'll do this one a little bit differently. I know I'm looking for exponential activity on top of 5. Well, I can write this in base 5 notation. That's 5 to the 3. And I think I know what can give me this right now. I think I know what gets me that. The activity, the cubing is in the denominator, and that's what that minus sign means. All right, so now we'll do it just mechanically. So 5 to the x equals 1 over 125. 5 to the x equals 1 over 5 to the 3. 5 to the x equals 5 to the negative 3. So positive exponents can be written as negative in the numerator. Okay, and so hence that answer. I hope that means more to you today than it did on Monday. I hope it means a whole lot more to you in December than it does now. 64 to the minus 3 halves. Oh, I think I know what that operation is. Numbers in the denominator are roots. And I know what the square root of 64 is. Square root of 64 is 8. 8 to the minus 3. Oh, okay, well, I'm not exactly thrilled to do 1 over 8 cubed, but that's 1 over 64 times 8, right? 8 squared 64, I gotta do another 8. And so that's 1 over 8 times 60 plus 4 is the way to do that in your head. There's your 480, there's your 32, there's your 512. Unless I made a careless error in my noggin. Which is quite possible because my noggin is getting very forgetful. All right, so we did that one in class, and that was just a little refresher of what you did because you're trying to put this in your long-term memory. All right, 3x minus 7 squared, and I said key moment. So I'm hoping we took the 3x minus 7 times the 3x minus 7 in class, 9x squared, and then our answer, we looked at it to see if there's a shortcut in doing it out this way. 3x times minus 7 is minus 21x. Minus 7 times 3x is minus 21x. Minus 7 times minus 7 is plus 49. We put it all together and we got minus 42x plus 49. Now the question is, could I get from here to here without having to do this all the time? This is called a binomial two-term square. Binomial squaring. What do? How do you get from there to there? Hope you see it. If you multiply these, if you multiply them, how would you get from there to there? You have to see it. And if you square that number, how do you get from there to there? I hope you're activating your thought process. All right, so we did that one in class. Open-ended question. So now let's see if we can do this without having to write it out from the last class. So what's the first thing you're gonna do? Well, you're gonna square this. And if you square with 3, you get a 9. And if you do x to the 4th squared, that's the same thing as x to the 4th times x to the 4th, which is x to the 8th. X to the 4th is 1, 2, 3, 4 times another 4, and just count them up. Count them up, you got 8 of them. All right, so that's x to the 8th. If you multiply, you get minus 6 x to the 4th a, which I'll write as a x to the 4th because it sounds better. And from the last problem, I hope you know you have 2 of these. And you can do it out over here. Go ahead and do it out, and you'll see that you have 2 of those, which means you have minus 12 of the product, ax to the 4th. And then you square the last term. And you found a nice quick way of doing binomial squaring. I don't think that necessarily that means much to you yet. Okay, so we'll have to develop what's going on here and why, but for now, just getting it started, getting the conversation started. Let's see what else we have. We have graphing form. Oh God, it's one of the most important topics we'll do all term long. Yeah, and I'm just going to do the mechanics of this and not talk about it too much because Don't want you working so hard at night. So we hopefully have started the conversation, minus b over two a. It's got geometric implications, it's got numerical, it's got graphical, it's got, most importantly, geometric, and I may have already said that 20 seconds ago. All right, so minus b over two a is gonna get us the x value of the vertex each and every time very easily. Minus b, 12 divided by 2 times a, which is also 2, gets me a value of 3. That means I can immediately say x minus 3 squared, because that's where we're going to get our smallest area coming out of this. This is an area statement here, area produced by side lengths. All right, so now if I put a 3 in, I got to know what comes out. So I guess I should put a 3 in here. That's 9 times 2 is 18, so that's minus 36, that's plus 7. When you put the first two terms in, you always get the opposite of the first. Minus 18 plus 7, so that gets me minus 11. So right now I have created a table where 3 gets me minus 11, and also up here a table where 3 gets us minus 11, which means that these are going to be expressions that eventually are equal. Okay, so what's the next thing I need? I need to know what the multiplier is here. Oh, I already have it. Oh, I guess I'm done. Let's just check it with another value. Let's check it with 0. All right, 0 is the easiest multiplier. So what's 0 do to the first two terms? Gone. Gives me 7. Well, let's go down here and put a 0 in just for fun. 0 minus 3, minus 3, minus 3 squared, 9. 9 times 2, 18. 18 minus 11. Oh, boy, I'm starting to get the same numbers out. Both calculations are producing the same inputs, outputs. I think they're the same. So what do we have? Oh, we can change this now to something we know. What did we put in? Oh, yeah, the critical number 3. What did it get me? Minus 11. That's nice. So if all of a sudden I went back towards 0 and I squared that, I should go up 9 units. And 9 units from negative 11 is negative 2. And that's, oh, shucks, that's not what I wanted. I wanted 7. Oh, well, let's go up another 9 units. It's up 18 units. Another 9 units. Oh, that takes me, oh, I guess I'd have to double that, because from negative 11 up to 7 is actually 18 units. But when I square 3, a change of 3, right? I'm going over to 0. I went up only 9 units. So what would I have to do to that 9 units to make it 18? Guess I'd have to double it. Okay. Now, we're going to be doing this every day till mid-December. It's going to mean more to you then. You're just starting to consider some topics here that took hundreds of years to develop. You're not going to get it in 2 or 3 days. Well, we're going to talk about it every day. Every day, yes. And so that's the one we did in class. And now I have to turn this over, but this is helping me immensely. Right, so we're just recreating what we did in class today. Trying to get the old long-term memory banks to start to recognize. Come on, get it. There we go. So now we have a square root function, which is the inverse of squaring. Right, so square root functions are things like 9. The input area of 9 gives me an output of 3, because the square root is the length of the side of a square. So 9 gets me 3, 4 gets me 2, 1 gets me 1, and 0 gets me 0. And negative numbers don't have square roots that are real numbers. I don't know what the square root of negative 4 is. God, we're going to have to talk about that, but not right now. So it looks like the inputs, 1 unit, then 4 units, then 9 units, get me jumps of 1. So 1, 4 is going to go up 1 from here. 9 units of change is going to go up 1 from here. We start to see that trajectory. All right. And the most important square root is 0. That's the minimum. So we'll come over here and we'll say, okay, we're gonna do a square root function, but we're gonna start from the number 9. And I want to get the square root of 0, but I guess I better write something like the square root of x minus 9. Yep, that gets me the minimum. Of course, I didn't want to get a 0 out. I wanted to get a 1 out. Okay, let's bring it over here a little bit more. Right now, a 9 gets me x minus 9, and I don't want it to be 0, I want it to be 1. And that's the beautiful thing about a marker. Let's see now. We're gonna change to the number 15, which means we're going, area is going up 6 units. So the area is gonna go up 6, but the side length is gonna be the square root of 6. Because that's what I'm measuring, the square root. I'm not measuring the area changed places. That's the area, that's the side length. Anyway, let's see. I'm not talking about this geometrically the way I want, but not going to start the video over, so that's numerically correct. I'm just going to say that for right now. And so where do I want to get to? Well, right now I'm starting at a height of 1, and I'm shifting that up how many units? I'm going to 11. You know what? I don't want that length. I think I got to go up 10 units to get to that. Yeah. So anyway, that's just numerically correct. I'm at a loss as to how to describe it without drawing more pictures, and I don't want to do that because of time constraints. So let's keep going. Now we're doing log base 4 of 64. I thought I already did those. Log base 4 of 1 over, I guess I'm just repeating for you. All right, so log base 4 of 64. So what's that saying? That's wondering what you put on top of 4 to get a 64. I guess I'm highlighting this because I want you to know that 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and 5 cubed is 125. And you need to become familiar with those values because you're going to use them a lot. And this is the one least likely to be understood or to be in your memory banks immediately. So that's why I put it there. So what do you have to do to a 4 to make it a 64? You have to cube it. That's the value of the exponent we were looking for. All right. And then we did 4 over 164. 1 over 64. Well, I'm hoping we're at the stage now, it's day 3, where you just know that the cubing takes place in the denominator. So that's just a conceptual opportunity to try to digest. And it may be there, it may not be, but we'll keep talking about it till it is. All right, 8 to the negative 2/3. Again, you can do this in any order you want. You could have flipped it, but why would you do that to work with a fraction? So again, go small, then big. Cube root of 8 is 2. 2 to the negative 2. I hope you're at this point starting to just say 1/4. That's where you're trying to get to. All right. And then we got solving right triangle, A equals 4, B equals 7, find C. I'm going to be changing this to X's and Y's. So let's let X equal 4. Let's let B become Y equals 7. And let's have Z equal the hypotenuse. All right, so I'm starting to hope that we can, I'll start rewriting these as X's and Y's because it'll lead us to vectors. And there's no reason you can't have a little chat about a vector at some point. Maybe not. That's some trig in it. So probably not. But let's get a 4 to 7 ratio. So there's 4, there's 7, there's your X and your Y, there's your Z. We're trying to find Z. And hopefully we've had the discussion in class about the Pythagorean relationship. 4 squared is 16. 7 squared is 49. If you add those two things up, you get 59 and 6 is 65. So therefore, what is that length? Square root of 65. All right, so doing Pythagoras is best done visually, actually seeing the square areas, how they interplay. The two little ones add up to the big one. 65 minus 49 gets you that one. 65 minus 16 gets you that, which means you can find those square roots depending upon which two sides I give you. All right, solving that triangle. Distance between 3,9 and 5,1. Well, distance between 3,9, let's just put a dot here. 3,9 and 5,1. Oh, okay, 5,1 is here. 5 is bigger than 3 and 1 is smaller than 9. Now, what have I really done? I've really created a triangle. Not necessarily drawn all that well. We're trying to find that distance. Well, it's exactly as the last problem. The only thing you have to do is recognize the size, 3 to 5, so that size 2. 9 to 1 is down 8. But it doesn't matter because we're gonna square. So if we square that, you get 64 units of change. If you square that, you get 4 units of change. So what is Z, or D in this case, the distance between those 2 points? Well, looks like I'm adding those up because this is the biggest one. So I'm looking at 68 units of area. So that distance is the square root of 68. Now we'll manipulate these things more later in the term. But right now, let's just get that Pythagorean relationship down because the whole study of trigonometry comes from it. And you're going to be studying that in the future. So you want to have a good feeling for these rates of change. All right, now we've got checking 2/3 x minus 8. Come on, marker, hang in there. That's a linear function. If I put a 0 in, that's the easiest multiplication to do. So 0 gets me -8, which is actually slope-intercept form, the intercept in this case being the y-intercept. And I'm going up 2 and over 3. So if I go over 3 units and I go up 2, I got a linear function that's increasing. Yeah, it's positive slope. And it's not going up at 1 to 1, it's going up at over 3 to 2. Over 3 up 2, over 3, over 30 up 20. It's a ratio of change, not that that's, the same as the unit sizes that I picked to work with. And now we want this thing to equal, what do we want it to be? We want it to hit a height of -4. Well, right here is -8, so -4 is right about there. All right, so what are we guessing? What are we guessing in terms of how much change that is? Well, I would say that I'm probably getting an x value, right? The x value. Well, it looks like it's positive. It doesn't look like it's that big. So I'm going to do this out. I'm going to solve it now, and I'm hoping I get a positive x. That's not too big. Okay. Let's find out. Oh, I got to add 8. Well, that's gone. Oh, I got to multiply by 3. Guess I've taken care of that. Guess I got to divide by 2. Well, what do you think? Is it a positive number that's not too big? I think I'm probably right. Of course, I could always check it. Let's put a 6 in. Oh yeah, 3 goes into 6 twice. 2 times 2 is 4, and 4 minus 8 is, I guess that was a logical way to do it. Right. Almost done here. Last one. Oh, thank God. Oh, 2x minus 5 squared minus 7 equals 25. I don't see any reason I can't do the same thing that I did in the last problem. I think I can add 7. 32, that takes care of that. I think I can multiply by 2. Oh, multiplication on this side, I guess I can divide by 2. I guess I can do that. I guess I can undo squaring. And so that's plus minus the square root of 16. All right, now I'll talk to you about the plus minus in class. And I guess that takes care of the squaring operation. And then I guess I got to add 5. Add 5 to plus and minus 4. And it sure looks like one of my answers is 9. 5 plus 4. The other one is 5 minus 4, which is 1. And at least I'm starting to put some inverse operations into my carpenter's kit. All right, so I don't know how long that took, but I'm going to be shortening homeworks as we go along, where I think I'm just going to do 5 problems that I think are most current, and we'll talk about that in class. Okay, ending the meeting.